Yeah, basically what I was going to do for today is talk a little bit about this wedge product, and kind of like set the stage for everything that we'll start doing after the break. So as I was saying, like the goal is going to be to analyze this ranking problem using some ideas from multivariable calculus. But for that, we need kind of like versions that can be defined on a simplicial complex or like a graph. So what I was mentioning, well, so last time what I said is that the cross product is not such a great operation on several fronts, but the wedge product is a good replacement for the cross product. So it is like a really useful operation. Like I think you kind of like come to appreciate it because it's one of the more powerful parts of linear algebra. And it doesn't take too much time to explain. It's kind of weird, actually, that neither of the undergraduate courses really does talk about it. Um, you almost have to take graduate level courses for it to be discussed. But okay, so what is the idea? If you have two vectors u and v, and you wanted to do u wedge v, right? So the way this will be interpreted is that, well, if you in terms of a picture, what you would draw is you make a parallelogram whose sides are the vectors u and v. So let's say that this is u and this is v. Okay, and the fact that you're doing u wedge v, let's see. Well, actually, let me draw them. I just want to get the orientation correct without issues. So let's draw you as the first one, like horizontally. Yeah, now this is better. So if you're doing u wedge v, what that means is that you draw the vector u first, and so here's the vector u. And then you just kind of like travel along the edges of the parallelogram, just like as dictated by the vector u. So if you have u there, then you have v. Let's say v was there, but then you just kind of like close the circuit, and then you kind of like go this way, and then you would go this way. Okay, so the way you think about this, you would call this an oriented parallelogram because you're kind of like traveling around it in a particular orientation. Okay, and in this way, you kind of like to emphasize the orientation, you would put kind of like something similar to what you do with angles, where you specify whether you're moving with when if the angle is counterclockwise or clockwise. So you do something similar for this. So, but the idea is that the wedge product, in a sense, is a parallelogram itself. So it is thought as a parallelogram. So it's kind of like a two-dimensional thing instead of like being a cross product, right? Because when you think about the cross product, in fact, if you remember from linear algebra or Calc 3 or a physics class, the cross product was a vector that's perpendicular to the parallelogram, right? So it's not like, it is related, but it's just that the cross product is represented by a vector perpendicular to the parallelogram. With the wedge product, you just keep the parallelogram itself, and you don't think about this like normal vector. Okay. Uh, and then the idea is that if you have done um, v wedge u, if you had done v wedge u, you still draw the same like parallelogram, But because it's V first, now you're moving in the direction specified by V. So V was pointing this way in my picture. So you start moving in the direction by V, and then you have to follow, and then with that direction, you just kind of like traverse the parallelogram or the edges. So now you would move this way. So the one that you write down first is the one that kind of like specifies along how you start moving along each edge. So you move now first along. Let me just write. You move first now along the vector B. That's the idea. So if you move first along the vector B, and then you travel the parallelogram this way, you kind of like see you're going in the opposite orientation or like the opposite way, right? So that is why you would say that U wedge V is negative of V wedge U. Okay. But it's kind of like similar. I think a good analogy to have in mind is similar to the angles. When you say like, oh, it's a 30-degree angle, that just means that you're moving counterclockwise. And if you say a minus or negative 30-degree angle, that's a clockwise angle. So it's kind of like a similar, if you think about this as being on the XY plane and you saw the parallelograms from like from the z-axis, you would see that in one version you were moving counterclockwise and the other one you were moving clockwise with respect to kind of like the positive z-axis. So, like this minus is kind of like reflecting the fact that, one is counterclockwise and the other is clockwise. So it kind of making sense. So in a sense, and I still, well, actually, in fact, the only two things that that this is like the beauty of it. The beauty is that the wedge product is completely specified by a few properties. Um, so, so the wedge product is specified by the following. So the only thing that's what's so nice because you just have to remember very few things. So this property that U wedge V is minus V wedge U. Well, kind of like as a special case of that property, but it's still worth mentioning, is that the wedge product of a vector with itself would be zero. So here by zero, I just mean kind of like the, you know, the zero parallelogram. So the parallelogram that has area zero, which is a point, right? So it kind of like looks like a point, so that's why I'm writing it as just like zero. But really, because we're thinking that the wedge product of two vectors is a parallelogram, by this zero, I mean the zero parallelogram. And the other one is that the other property of the wedge product is that you can distribute with it. So if you have the wedge product of U with V1 plus V2, this is U wedge V1 plus U wedge V2.
So is it type of the wedge product just like a combination of four vectors?
Did you say for vectors or?
What is the type of like wedge product? This is also a vector.
Oh, no, no. So it is, so if it's the wedge product of two vectors, right, which is what I'm doing right now, I mean, actually, they are called bivectors. So they're not being thought of as, they are not regarded as vectors. If by vectors, you mean like kind of like an arrow, right, like in space. Like if you want to think about this geometrically, they literally are just the parallelograms together with a particular way that you're moving along the parallelogram. So, but it's really kind of like two-dimensional. Like that's the difference. Because when you're doing the cross product, right? Like the cross product was a vector, was kind of like an arrow perpendicular to the parallelogram, but the arrow itself is kind of like one-dimensional, right? Because it's a segment. But the wedge product of two vectors is itself kind of like the parallelogram with the extra added property that you're moving along this parallelogram in a specific way. But it is kind of like so it's definitely not a vector, although all these they're called like bivectors, but all these bivectors do make up a vector space in the same way, in which all the 3 by 3 matrices make up a vector space, right? So in this like broader definition of a vector, that a vector is whatever is an element of a vector space, they are vectors, but kind of like in the more narrow sense, where it's like, oh, I want to think of a vector as an arrow. They are not arrows because they're two-dimensional, if that answers your question. But they will make up a vector space, right? So in that sense, you're still allowed to call them vectors, but not in the usual physicist way of thinking, oh, of a vector as an arrow. Those are definitely not. Yes.
We have like three vectors,
Mhm.
would be like a cube.
Right. Actually, that's where I'm headed with next. So, but the fact that the idea, the decision to kind of like increase the dimensionality is what fixes all the issues that the cross product was giving us. So the fact that when we kept insisting that the cross product had to be a vector, when you started with two one-dimensional things, was that is where you get stuck and that creates issues. But yeah, actually, I want to just show you like a formula here first with this, so that you see that it's super elegant. So imagine that this is really fun because you don't. The beauty about the wedge product is that you don't have to remember almost anything. That's so cool. That's what's so nice about it. Everything kind of like follows, kind of like like becomes really really straightforward. So imagine you had a vector u. And I'll write it as U1, E1 plus U2, E2. So I'm going to write E1, E2 instead of I and J, but you can think about them in that way. And then what is V? V is V1, E1, right? Plus V2, E2. Okay. So again, U wedge V is kind of like this oriented parallelogram, which is again like their official name, or they also get called by vectors sometimes. Um, but I want to find a more concrete way to understand this. Okay. But again, like this is what U wedge V represents. And this is all two-dimensional, so the parallelogram is two-dimensional. It's being drawn on the plane. But let me find an expression for this, which is like a little bit more interesting. So, so the idea is that you kind of like rewrite each vector in terms of the vectors I and j, right? And then, so the wedge product, it is similar to like the regular multiplications that which are distributive, like all the ones that you have seen in your like education, multiplication of numbers, dot product, cross product, multiplication of matrices, they are all distributive. So um, that's what you would call, like, if you want to be more technical, that's what you would call like a bilinear operation, like the fact that you can kind of like distribute it in that way. But what that just means is that you can FOIL if you want to kind of like be very pragmatic about it. So it's just, uh, let me write it like this. You want. and just put in a bunch of stuff which I'll complete. Sorry, this YouTube should not have anything like this. And then to E2, so okay, so it's going to be like this. And let me move this a little bit further. Okay, so let me just write everything first, and then I'll show you what what's happening here. E1, 2, and then one, 2, and this U1 should have stayed as U2. And this one should have an arrow, and this one should have an arrow. Okay, so what's happening here? So if you distribute, this should be this thing wedge, this thing. So it's U1 V1 times E1 wedge E1, okay? Plus, then the first one wedge, the second one here, right? So that's U1 V2, and then E1 wedge E2, plus then the second one wedge the first one, so that's U2 V1, E2 wedge E1, plus the second with the second. So U2 V2, and then E2 wedge E2. Is that okay? Is that okay?
Yeah, so here piece, the fact that you can like pull out a scalar.
Right, and then you could also pull out the scalar, right? That's kind of like the bilinear part, because linear means that it's kind of like, like the linearity is what allows you to pull out scalars, and bilinear just means that you're doing it because like, from each, you can pull out the scalars that appear on the left or on the right, kind of like, on each of the factors.
Is the distributivity also kind of like linear?
Yeah, so the thing is like, usually when you, right, like a distributive properties in a sense, linear in a way, one factor at a time is kind of like a linear operation, right? Yeah, yeah, yeah. Because in fact, like, well, I'll erase this, but that's actually, if you write a matrix, for example, times two vectors, right? That is AU plus AV. Right, but there are two ways to think about that. That's kind of like the linear property of the linear transformation, or that's also just like the fact that you can distribute, right? So they're kind of like both become indistinguishable. Okay, and then what happens that kind of like, again, you don't need to know anything. You just have to know the defining properties of the wedge product. So the defining properties is that the wedge product of any vector with itself, the wedge product of any vector with itself is the zero parallelogram, right? So these two go away because they're going to be the zero parallelogram, and you don't care about that. And then you can use the fact that it's the fact that anti-commutes, meaning that u wedge v is minus v wedge u, which is the same that you had with you know that's the same that you have with the cross product, right? So this gives you minus E1 wedge E2, right? But so what do you get here? You get, if you notice of the things that survived, what are the things that survived? The E1 wedge E2. Oh, I'm sorry, I should. Oh, yeah, like it's the same. It's E1 wedge E2. So let me just put it in black, just because it's the same color. No, E1 wedge E2. And then what do you have inside the parentheses when you factor out the scalars? You get U1 V2 minus U2 V1, right? But what is that? That's the determinant, right? If you stack the vectors as the two vectors as a 2 by 2 matrix, right? That tells you that U wedge V, right? That this is uh, the determinant of U1, U2, V1, V2 times E1 wedge E2, right? And what is E1 wedge E2? That's the standard unit square on the XY plane, but traveled in the, in the contact, what is this thing? That is literally a square, this is the square E1 wedge E2, right? So that is what this corresponds to, like the unit square. So this says that the wedge product of two vectors, right? It's kind of like a deformed version of the unit square, right? Like you kind of like deform it, take the unit square and it gets stretched out until it becomes the parallelogram, right? And the conversion factor is the determinant of this 2 by 2 matrix, which is why if you take linear algebra, they tell you that the determinant of a 2 by 2 matrix is the oriented area of a parallelogram, right? Or they also tell you that the cross product, if you think about this is also the formula for the third, like if you had taken the cross product of the two vectors, you would have found the same expression times the vector k instead of like this like wedge product instead of like the unit square. So it's very, you see, it's kind of like a cousin of the cross product, but it has a slightly different interpretation because again, this is being regarded as an equality between two-dimensional objects. So again, this is like the difference is that now we're dealing with two-dimensional things, whereas with the cross product, we always try to turn things into vectors. We always try to make things again into vectors. Okay, so the wedge product just kind of like says no, it's more natural to just think about them as being two-dimensional quantities. See, and the fact that the determinant when you swap the rows you get a minus sign is consistent with all this with this property of the cross product. Sorry, of the wedge product. Uh, so it gives you, but again, like you could, if the kind of like the formula for the determinant pops out like from here, like, you didn't have to remember it, like, you start using the distributive property and like those other properties of the wedge product, and that gives you what you want. Okay. Yeah.
So just like, the scaling, does it mean anything, or is it just like useful mathematical notation?
When you say the scaling,
So it's like, the E1 wedge E2, that's like the unit square, right?
right.
So then if you're scaling that, does that like have any useful
Oh,
interpretation, or is
well,
that
right.
like the factor notation?
Yeah, no, I see what you're saying. Right. Oh, yeah, what this means, like, in fact, this is kind of like the change of variables formula from Calc 3, right? When you multiply, when you switch to Cartesian to polar, or when you would get RD theta, right? So, what that means, like, no, like it does have like an interpretation because like, okay, this has like the unit square, right? Obviously it has like area 1, right? Let's say that, for example, with our wedge product, like the area of the parallelogram had been like 3, right? Let's say that the wedge product, sorry, that the parallelogram determined by U and V had like area 3. So the scaling 3 pictorially, I mean, just means that, like you could fit 3 unit squares into here. Well, I'm not doing a perfect job, but some of them may need to be broken, right? So that the area kind of like, maybe the area was a little bit bigger here, how many full unit squares do I have? Like 1, 2, 3, 4. Maybe these two make a one together, right? So 5, and let's say 6. So maybe this parallelogram had like area 6, right? And so the scaling factor tells you that, yeah, if you kind of like you can, if you are willing to kind of like cut the unit square into pieces, like as in here, you could fit 6 unit squares. But yeah, in terms of shape, you do have to, you know, like you cannot figure out the shape just from knowing that it's 6 times the unit square, right? Like, so you do have to remember what the original vectors were, right? But it does have some interpretation because which is it's actually how the Jacobian, that is what you call the Jacobian in calculus 3. It is essentially it is really kind of like a wedge product in a sense, like, it's just that it's because if you think about this, actually that is like the best way to understand integration. But when you have something like dy dx, right, equals sorry. The thing is, like, in Calc 3, the way things are written is something like dy dx equals r dr d theta, right? But it's really the correct way to write it. And this is what you do in differential geometry. You would write this as something like dr wedge r d theta. And so the idea here is that, again, dy dx is kind of like a unit square on the plane, right? So this is still kind of like dy dx kind of like are similar to E1 and E2. They're called differential forms, like in differential geometry. And then dr d theta, so the r is the r would, when you have like in polar coordinates, something like this would be the r, and r d theta was roughly, well, kind of like r d theta would be something like this. So if you take the wedge product, well, of course, like, it's kind of like infinitesimal, so it really shouldn't look like curved. But all, like, what I'm saying is that, kind of like the change of error formula says that, like, those two things kind of like really basic. Um, But yeah, so like when you do all these things in multivariable calculus, there is like a more elegant way to do it with like this like wedge product business. Um, and then with three is what you kind of like already like anticipated, right? Like with three vectors, you can make a parallel pipette, right? Kind of like a tilted, a deformed box, right? It's kind of a slightly slanted. So if you had U, V, and W, right? Did I change? Oh yeah, U was blue. So let's do it. And if you had U, V, and W, then then the wedge product of U with V with W is kind of like an oriented parallelepiped, right? So U, V, so this like wedge product of, but the point is that it is three-dimensional. That's the difference now, that this is three-dimensional. Okay. And then this would be kind of like the oriented, this would be an oriented parallel. And as you may guess, if you gave entries, like say if these vectors were in 3 dimensions, right? In R3, so it has like U1, U2, U3, V1, V2, V3, and W1, W2, W3. It's kind of like you can check using the distributive property that what you find is that the formula for this is the same as the determinant of U1, U2, U3, V1, V2, V3, W1, W2, W3, times E1 wedge E2 wedge E3, which now would be the unit cube, right? The standard unit cube. So that's where that's where the determinants of matrices pop from. Yeah.
Doesn't this mean that every wedge product is the same except the area?
Well, in 3 dimensions, um, when you say the wedge product is the same, you mean or how are you thinking about it?
Any choice of UV and W, they're all like.
Oh, right, because yes, because but only because now I'm thinking of the vectors in 3 dimensions. So for example, I'll do one in R4. So in R4, then now you have like different possibilities, right? Because it's 3 chooses 4, like in this combinatorial, yeah, in on R3, if you have three vectors, their wedge product would be a scalar multiple of E1 wedge E2 wedge E3, right? That is correct. But for example, in R4, right?
Oh, so you look at what problem two vectors are.
Right. Yeah. So actually, I'm glad you bring this up because it's also useful to write everything in R4, because you know 4 is an important dimension because of like space plus time is 4 dimensional. So it's also useful to know how things look on R4. Um, you know, but yeah, in R4 you have like 4 standard unit vectors, right? So that's kind of like so the space of vectors is 4 dimensional in R4, but then how many wedge products can you do, which are interesting, right? You could do E1 wedge E2, right? You could do E1 wedge E3. You could do E1 wedge E4, right? What else could I do? I could do, okay, so I'm not counting E1 wedge E1 because that's 0, right? So you don't care about that one. Then with E2, you could do E2 wedge E1, but that's kind of like minus E1 wedge E2. So it's not really too different from the other one. Then you could do E2 wedge E3. That's kind of like genuinely new, right? And then you could do E2 wedge E4, or you could do as a last option E3 wedge E4. Right? Because all the other wedge products between the basis vectors are either 0 or like are minus one of the ones that I just wrote. So how many possibilities did we get? We get 6, but 6, if you have seen this combinatoric symbol of like n chooses k, that's 4. I just don't remember if you say 4 chooses 2 or 2 chooses 4. I don't remember like the correct term. And chooses k, I guess n is larger than k. So this is like 6 options. But that's 4 chooses 2. In combinatorics, that just means 4 factorial over 2 factorial times 2 factorial, right? And yeah, that should be 6 because this is 4 times 3 times 2 divided by 2 times 2. So yeah, that gives you 6. So those are kind of like all the that's actually an interesting thing in 4 dimensions because you cannot visualize this too easily. But in 4 dimensions, you have an x-axis, a y-axis, a z-axis, and a w-axis, right? That's 4 dimensions. And then and on R3, you have the xy plane, the xz plane, and the yz plane, right? So you have 3 kind of like standard planes. And so here, what I'm saying is that in 6 dimensions, sorry, in 4 dimensions, you have 6 standard planes because this would be kind of like the XY plane, or this would be related to the XY plane, this one to XZ, this one to XW, then this one is YZ, then YW, and then ZW planes. So, or it's unit squares if you like. So in 4 dimensions, there are kind of like 6 basic unit squares that you can build, and any other parallelogram in 4 dimensions is kind of like a linear combination of those 6 unit squares, basically. That's the idea. Um, and then in let's see. So in fact, like so what this means is that there are six basic unit squares in 6 dimensions, in 4 dimensions, sorry, in 4 dimensions. And any other parallelogram, if you use a wedge product, can be expressed as as a linear combination of these 6 basic ones. And any parallelogram.
You say parallelogram, do you mean like any like n-dimensional parallelogram?
Oh no, I do mean here parallelogram is in the sense as 2 dimensional. Like I am reserving the word parallelogram for something 2D for sure. Yeah. Not the yes. And then how many unit cubes, right? How many unit cubes are there in 4 dimensions, which are generally different? So you could do, for example, you could do E1, wedge E2, wedge E3. You could also do E1, wedge E2, wedge E4, right? Then you could also do so so you could do E2, wedge E3, wedge E4, right? And those let's see, I think if I if they have to be the wedge product of 3 vectors, so I can, I have 4 options, so I can remove one at a time. So here I removed E4, here I remove E3. Which one am I forgetting? 1, 3, 4. Oh, thank you. Yeah. So E1, wedge E3, wedge E4. No, sorry. You said, oh yeah, because I wrote E2. Right. Now I see it. Right. Because right, if I give you 4 options and you have to take the wedge product of 3 of them, then that means that you have to leave one behind. Right. So in the first possibility, I didn't use E4. Here I didn't use E3. Here I didn't use E1, and here I didn't use E2. So that's kind of like saying each of these 4 is kind of like a unit cube. Each one is kind of like a unit cube in 4 dimensions. So they're kind of like 4 basic unit cubes in 4 dimensions, and any other parallel pipette is a linear combination of these 4 basic ones. So there are 4 options, but what are these 4 options? There's 4 chooses 1, or like again 1 chooses 4, like I don't remember how to say that, but it's 4 factorial over 1 factorial times 3 factorial, and that's that is 4 basically.
How would you show that these are actually independent?
Well, okay, so let's see. So I'm just trying to say if like you can do. Let's try to think about it. On R3 there like E1 wedge E2, E1 wedge E3, and E2 wedge E3, right? So let's just go back to R3. So you have E1 wedge E2, E1 wedge E3, right?
With your tensor product, it's easy because you have an realization.
Right. Like that's what I'm actually thinking. Whether I have how much like of a how much of an intuition you can just how much do you really have to rely on the formal construction to show that. But right, like because if you had like a linear combination like this, right? Well, yeah. No, what I was thinking more is like if I want to show that ABC have to be 0, right? Like the only way to get so if what happens Right. Yeah. What you do is you start wedging with one at a time. So, for example, if you wedge both sides of the equation with E1, right, you get A, E. That would force that C equals zero, right? You see where I'm going? Let me write it. It's kind of fun just to see how much can you do without using the formal definitions. But let me show it for everyone because like it may not be clear what I meant. No, this is really fun part. I think I remember when I learned this for the first time. I was like, "Oh, this is some of the best thing I ever learned about linear algebra." I think there's really like a magic to this is called the exterior algebra. This was invented by Grassmann, who was like actually like a German mathematician, but he was like a high school teacher. So he never got like a permanent university position in Germany. And in fact, when he died, he wasn't not like famous. Like it wasn't until a couple of decades later then like people realized, oh, this thing that he developed was like a really interesting stuff. So it's one of like these people who like made like major discoveries, but never really, he was just like a regular. Well, of course, like that's like a very weird, like like to have like a high school teacher who was developing all this stuff, like. So there were like some German professors like back then in the 19th century, which was like.
It's like tensor product or it's like some universal object, so it's like every wedge product is isomorphic. Or
Well,
there's kind of like multiple wedge products in the same space.
no, well, no, like if you like, uh, well, if you realize a wedge product, in terms of the anti-symmetric algebra of the tensor, because it's what we were talking about at the end of class last time. You can identify the wedge product with kind of like the subspace of two symmetric tensors.
Oh, I guess it is.
Yeah. So I guess you could say that there's some universality to it, which is inherited just from the universality, of the tensor product construction. Uh, but well, so basically what we were sorry, just to kind of like give some feedback on what's happening here. Actually, let me. So I haven't really said this too explicitly, but what I want you to think of these wedges are like genuinely like as kind of like independent of one another. And so, for example, E1 wedge E2 corresponds to this like unit square on the XY plane in 3 dimensions, right? If you call this like X, Y, and Z, like X, Y, and Z, and this one is called X, Y, and Z, right? E1 wedge E2 is a unit square on the XY plane. E1 wedge E3 would be the unit square on the XZ plane, right? And E2 wedge E3, right, would be the unit square on the CY plane, right? So, just based on how they're positioned in space, you would want to say that they're kind of like linearly independent in some way, right? Because, knowing this one shouldn't tell you anything about the other and shouldn't tell you anything about the other in the same way which I, J, and K represent kind of like different directions in space, right? So what I'm trying to say is that these unit squares kind of like represent different directions in the space of all parallelograms, right? Which is a little bit more abstract, right? But so that's kind of what I'm kind of corroborating here more algebraically, because if you remember that what was it? Just a little bit of a throwback to 50, right? Like what is the definition of linearly independent? If you have things that are linearly independent, that means that when you take a linear combination of them, that gives you the zero vector. The only way for that to happen is that if each of the coefficients in the linear combination is zero. So that's what I'm saying here. And let's suppose you had a combination of these three squares that gives you the zero square, right? And this zero is the zero square. Like that's where the zero has multiple meanings, you know. So this is the zero square. So I'm saying like if you could somehow like abstractly add these squares together to get the zero square, the only way for that to happen is that each of them was rescaled by zero, right? And how do you see that? Well, it's kind of like similar to a dot product or a cross product. You can just wedge every side of the equation with E1. So when you set wedge every side of the equation with E1, obviously you're having E1, E1, E3 in black still. You know, when you wedge everything with E1, this goes away because it's E1 wedge E1. There's an E1 wedge E1 here. The only one that survives is the last one because it has three distinct ones. So that tells you that C times E1 wedge E2 wedge E3 had to be zero. But now this zero is not the zero of a square, it's a zero cube, right? Because you see like the now it's a zero cube. So that's where like you have to come like if you're keeping track of the dimensionality, um, you have to think about that. But again, the only way for the unit cube times a number to give you the zero cube is if that number was zero. Okay. And so that's how you find the C equals zero, and then you wedge everything with E2, and then like instead of wedging it with E1, then you wedge with E2 and then with E3, and that's how you get that the other two coefficients have to be zero. So it's like a very clever argument, uh, to show that there's kind of like a linear independent, like so the squares in a sense are kind of like linearly independent, these ones. So that's why I was saying at the beginning of the class that you can really think that there you have like a vector space of squares or like of parallelograms. So there, in the same way in which there's like a vector space of arrows or lines, there's kind of like a vector space of parallelograms, and then there's a vector space of parallel pipettes, and there's a vector space of hyperparallel pipettes, and they have like a basis, and the bases are kind of like these unit squares or unit cubes or unit hypercubes, however you want to call them. But the beauty of the wedge product is that it makes everything very transparent, because it's very easy to get confused, like when you're thinking about higher dimensions and like all these higher dimensional objects living inside higher dimensions, you see. So similarly, you would find that P equals zero. Okay, and maybe just to go back to finish this page, what I was saying is that, for example, in R4, there are kind of like six distinct unit squares, and any parallelogram is a linear combination of those six unit squares. There are three distinct unit cubes, so there are three unit cubes. Sorry, four distinct unit cubes. So four unit cubes. And any parallel pipette is a combination of these. And there's only one which you call top dimensional when it's in R4, which is E1, wedge E2, wedge E3, wedge E4, right? So that's a only four-dimensional hypercube in four dimensions, which kind of makes sense. So there's only one that. So that's the one that's maximum dimension. Only one. Because again, any other possibility is kind of like plus or minus this one, depending on the number of permutations that you do. How many swappings you do. So that's 4 chooses 4, which is 4 factorial over 4 factorial, which is 1. So in fact, the formula, the general formula is that if you have on Rn, right? So this is like the general formula for Rn. Is that if you live inside an n-dimensional space, the number of k-dimensional distinct objects, k-dimensional parallelograms are like, is n chooses k. So, there, and then you look at the k-dimensional parallelograms, meaning that the ones that are like a wedge product of k vectors. These are they make a vector space of dimension n chooses k. So make a vector space. And sorry, for those who have not seen this formula before, this is like one of like this. If you ever take a course in probability theory or combinatorics, this is like bread and butter because all those problems usually involve this like in some way or another. But this is defined as n factorial divided by k factorial times n minus k factorial.
The three-dimensional case, you did four choose one, did you mean four choose three? I think they were gonna be the same number by chance.
Sorry, for the three dimension. Oh, I see what you're saying. Yeah, I meant yes, but they agree because of the symmetry, right? Like there's actually a symmetry, which was what I was going to mention next. But I'm glad that you noticed this. Yeah, this would have been four chooses three, or choose like three chooses four, whatever this is. No, but yeah, there's a symmetry that n chooses k is the same as n chooses n minus k. Right? And so there are as many k-dimensional things as n minus k-dimensional things. So they are kind of complementary dimension, you know. Which in three dimensions, there's a coincidence that happens, and that kind of like solves a lot of the conundrums of how like the magnetic field behaves, and this thing about that I was mentioning last time about pseudo vectors, because in three dimensions, right, what happens in R3 in n equals 3, right? Then you have the 3 chooses k is the same as 3 chooses 3 minus k, right? And really like the possibility that's interesting is like with k equals 1, right? And so that gives you the 3 chooses 1 is the same as 3 chooses 2. So that means that there are as many, one-dimensional things as two-dimensional things. So again, this is kind of like the what is like the 3 chooses 1? That's like I, j, and k, right? So these are like, or like E1, E2, E3, right? Right. Which is the space they're used to, right? But and then how and then these are like the two-dimensional or the well, two-dimensional squares is a little bit redundant, right? But I mean like these unit squares that I was talking about. So this is a unit square on the xy plane. This is a unit square on the zy plane. And this is the other unit square in the XZ plane. So the reason why I'm using this color matching, because again, they're like both three-dimensional spaces. So any two vector spaces of the same dimension can be, there's kind of like, can be put in bijection, that's the name for it. But the idea is like, how do you match each one with which? So like the idea is that you associate to one of the basic vectors, like the unit square that is in the plane perpendicular to that basic vector. So the matching gets done in terms of like the perpendicularity. So the blue vector, which is along the y-axis, is perpendicular to the xy plane. So that's why this one gets matched with that square. And the purple one that is perpendicular to the xy plane, that's why it gets matched to the to the purple square that you see there. And that's like the reason of that connects all this with the right hand rule and everything, because if you think about doing the right hand rule, E1 cross E2, like it's kind of like pointing out this perpendicular vector. So all of it kind of like fits very nicely. But the idea is that there are certain objects, like the magnetic field, that really is better understood as a wedge thing, as a wedge of two vectors, but because of this coincidence, that's why it gets identified with a vector. So that's why you talk about the magnetic field as a vector, but it's really more like a bivector. So that that is like so it's only because in dimension three, if you lived in a four-dimensional world, you would have called, spatially, I mean, you would have identified the magnetic field as a bivector, or in six dimensions, in a six-dimensional world, the magnetic field would have been a bivector and so on. So like that's kind of the like at least if you use like the usual formulas for like the Lorentz force and all this stuff. So really like the magnetic field is a bivector, but because of this coincidence, like that's why it's thought of as a vector in the traditional physics courses, because of this coincidence, the three chooses one is the same as three chooses two, which is crazy.
The fact that you can form a bijection.
Right, it's because you can form a bijection. Yeah, yeah. That bijection in general is called the Hodge star. There's a formula that gives the bijection, and it's called the Hodge operator, like the Hodge star. Um, but yeah, that's kind of like the reason for that happening. Um, of this bijection between the two spaces. Big bijection.
Generally, like a sense of like orthogonality between like parallel.
Right, exactly. In a sense, yeah, exactly. Like, you would say, like, for example, all these three would be regarded as orthogonal to one another, and in fact, orthonormal, because they're the unit squares, right? So they are, in a sense, like orthonormal vectors. I mean, one way to do that, like, you can cheat. Once you know that they are in bijection, you can just transport the dot product from this space to this one if you want. But if not, you can just declare them to be if you have like the standard unit vectors on our end, those are orthonormal under the standard inner product, and then you declare the wedge product of k of them to be orthogonal to any, on, so yeah, it's kind of like, by default, like, you kind of regard them as perpendicular. But it is corroborated, but even before you do that, it is useful to go over this stuff that I was saying, that where I was doing the linear combination part, because one consequence of being orthogonal is that they're linearly independent. So you better know, better be convinced that they should be linearly independent. And once you do that, it's kind of like adjusting them so that they kind of like become perpendicular. So and now, maybe just to, okay, how does this connect to calculus? And like the connection to calculus is very interesting. It's very cool. So let me at least mention some of the beginnings of this. But it's really like magical how easy everything becomes. That there's always like a couple of years there's someone who wants to write like, oh, we should teach multivariable calculus using like all this wedge product business, and then you backtrack because you are like, oh yeah, but now, like, it's too hard to change, like, just like the fact that like all the textbooks are written in a particular way. But if you were able to do this with like, if the course like started with wedge products, there are so many things that would simplify, which is like, it's such a tremendous simplification that it's hard to kind of like even conceive of it. So the idea is that the gradient, the curl, and the divergence, they can all be summarized by a single formula using the wedge product, which is insane. So I'll show you how it all looks in R3. So So I'll show you how the gradient, the curl, and the divergence look like from the perspective of this wedge product. And again, if someone wants, I'm just giving you the basics to motivate how you should discretize these formulas on a simplicial complex. But if someone wants to learn more about this, this is what's called like differential forms. So you know, like the full topic, which I'm not going to go into, but the full topic is called like called differential forms. Okay, but the only thing that the magical thing that you have to remember is the following. So if you have, again, I'm just going to do it on R3 because that's like what you're more familiarized with. But so if you have on if you have something on R3, if you had like a function of R3, right? If this is like a scalar function, uh, then whenever you have a scalar function, you can find something that's called its exterior derivative. That's just like a fancy name, okay, which I'm going to call df. So I'm going to call it df, but it kind of like looks similar to the notation for differentials from calculus, right? But this is now called like the exterior derivative of f. And just by definition is, okay, the function is a function of R3. So essentially the way you define it is that the derivative of f with respect to x times E1 plus the derivative of f with respect to y times E2 plus the derivative of f with respect to z times E3, which is just what you would have called before the gradient, right? It's what you would have called the gradient in previous lifetimes, right? Like this is just like the gradient of the function f, but it now has like this fancy name, right? It now has this fancy name of being called the exterior derivative. But it does reproduce the formula for the gradient, basically. Now, so that's okay. The place where this gets fun is, okay, this, how you would define this for a function. Now, imagine I have given you a vector field, right? So now let's say I give you a vector field, and now you'll see what, I think at least I'll do this, I'll finish this after the break, but at least I have enough time to show you what happens here, which is really fun. So now you have a vector field. If you remember what is a vector field, you know, it's a vector, you know, but where the vector depends, you know, the actual vector depends on the point in space, right? So meaning, so what I'm trying to say is that this is a vector, right? Because it's something that's a combination of E1, E2, and E3, right? But the only difference with a regular vector, right, where like a regular vector, like the coefficients are always constants, right? In a vector field, the coefficients are, you know, in a vector field, the coefficients are like functions of x, y, and z, right? So my claim is that the exterior derivative of this vector field is defined to be F1, F2, F3 just refer to the first, second components, first, second, and third components of the force. I'm using capital F, uppercase F, because I'm thinking of it as a force field. You know, that's why I'm calling it uppercase F. But the idea is that the exterior derivative kind of like is defined almost like as if this were distributive. You just multiply by d every single one of them. So you do d of F1 wedge. That's like now that's the magic. You do D of F1 wedge E1 plus D of F2 wedge E2 plus D of F3 wedge E3. And you'll see something really fun. So you just take the D of each of them, right? But the thing is like D of a function, right? F1, F2, and F3 are functions. So when you take their exterior derivatives, you get a vector, right? So you cannot write like a vector times a vector. You have to put like which operation you want to do. So I want to do wedge between. Okay. And you'll recognize what I want to do in the remaining 10 minutes is work it out, and you'll recognize a familiar quantity, hopefully. Okay, so let's work this out. What is again, what is the exterior derivative of a function? Is the formula that I just wrote. You just take the partial derivatives of the function with respect to each variable and wedge times the corresponding unit vector. So this would be okay, this is going to get a little bit messy, so I'll just write it in 3 lines. Okay. Then you do the same for F2. And then you do it for F3. So I'm just taking the gradient of each of the functions, like the components of the force, that's one way to think about what I'm doing here. Sorry, the last one, I think the first one I forgot to put a E3 here. Just let me move it because this one should have like an E3. All the others are fine. Okay, now let's continue this in the next page. I'll copy paste this just to make it a bit more clear what's about to happen. So what would you do in the next step? You would distribute, right? In this case, you would distribute, you do this one, wedge, this one, wedge, this one, wedge, this one, and then you do the same with the others, right? This one, wedge, this one, wedge, this one, wedge, this one, and then this one, wedge, this one, wedge, this one, and this one, wedge, this one, right? But there's some that are automatically ignorable, right? Because E1, wedge E1, you can ignore. You can also ignore E2, wedge E2, and you can also ignore E3, wedge E3 because of what we were talking about before, that the wedge product of a vector with itself does not matter. So basically, just to kind of like, I'll write it down again. This one, I don't care. I don't care about this one. I don't care about the last one. And then I'll just distribute everything else, okay? So then this one gives me, this one also got wedged with E1. The other one also got wedge with, this one also got wedge with E2. And now each of these got wedge with E3. Okay, so far so good. How are we doing? And now really comes the fun part because you have six terms, right? But you can factor two at a time because, for example, E1 wedge E2 and E2 wedge E1 are basically the same except for the minus sign, right? So I'll kind of like group them in terms, like group them in pairs. Sorry, I meant. I'll group them in pairs, and then you'll see the miraculous thing that happens. Okay, so let me, and this kind of will be almost the last thing I do for today. But so just to indicate how I'm pairing them, I'm going to use the same color. So I'll pair these two together. I'll pair these two together. And I'll pair these two together. So let's see what happens. So if you do all of that, then the exterior derivative or like the differential, that's another name for this. Well, no, the exterior derivative, I guess, is more common. So it would be the derivative of f2 with respect to x minus the derivative of f1 with respect to y times E1 wedge E2 okay. Then what are the purple ones? The purple ones are the derivative of f3 with respect to x minus the derivative of f1 with respect to z and then that is with E1 wedge E3. And the last one is the derivative of f2 with respect to z. I'm going to do E2, E3, wedge E3 actually. So I'm going to do the derivative of f3 with respect to y minus the derivative of f2 with respect to z, and that is E2 wedge E3. Is that okay? Is that making sense? Huh. Do anyone recognize this interesting combination of partial derivatives? What is that?
Curl.
They are basically, if you want to go through the definitions of the curl, you end up find up to a sign. It could be plus or minus, like you do have to kind of like do the matching properly. But those are basically the combinations of partial derivatives that appear when you do the curl of a vector field. So the curl kind of like pops, if you apply this formula for the exterior derivative, the kind of like the curl magically appears. So, each of these entries can be identified with one of the entries of the curl of f. Corresponds to an entry of the curl. Huh. But you see, like the formula, it's not that you had to memorize much. It's just like you just took the exterior derivative of each end of each function, which what you had next to it. And the divergence essentially can be done in exactly the same way, which I'll probably tell you more after this a spring break. But what I'm saying is that this kind of like starts answering our conundrum because the idea is that the curl is actually better understood as a bivector, and these entries will become like entries of a skew-symmetric matrix. So there will be a representation of this in terms of skew-symmetric matrices, which will be convenient. And once you have something of that sort, then it is more clear how to discretize it. And then we'll have kind of like a discrete version of the gradient on a graph, a discrete version of a curl on a graph, another divergence on the graph, and that will is what we will need for doing this ranking thing that I had mentioned on Tuesday. Okay, so let's end here, but hopefully this gives you a small appreciation for how this wedge product is very convenient. But we'll continue talking about this on Tuesday, but we're almost done. But I thought it was useful to go into this in a little bit of depth because it's like really one of the more useful operations in linear algebra. Is kind of like a shame that it's not sometimes like covered in an earlier class. So yeah, let's stop here. That sounds good. And try to break it.